So hey everyone, today we'll discuss the next question of a DP sheet, flip and adjust. The problem states that there are n cards with an integer written on each side. Card I has an integer AI written on the front and an integer BI written on the back. You may choose whether to place each card with its front or back side visible. You need to determine if you can place the cards so that the sum of the visible integers exactly equals s. If possible, find such a placement as well. The constraints are n is only till 100 and s is still 10 raised to power 4. We'll see how it helps us further in building up our solution. So coming to the format of the output, if the ith card should be placed with its front side visible, you need to output an H. If it should be placed with its back side visible, we need to output a T. So let's understand the question better by solving for this sample input. Okay, so here we have been given n equals 3 and s equals 11. And we have three cards with integers written on the top as 1, 2 and 5 and integers written on the bottom as 4, 3 and 7. Top is denoted by a H in the answer and bottom by a T. So out of all possible combinations, one such arrangement for our answer is definitely the first card facing upwards and second and third facing downwards. So this gives us a sum of S equals 1 plus 3 plus 7, which equals 11. And the arrangement is H, T and T, right? Another such arrangement is the second card with its bottom part of a bottom integer visible and the second and third cards with its top integer visible. So again here we get a sum of 4 plus 2 plus 5 equals 11 and the arrangement is denoted by THH and that's exactly given in the answer to our sample input. So if there are multiple arrangements possible, we can just output any of it. Also, first of all, why it's even a DP solution, right? So say consider for the first card, there are two possible outcomes. Either the top part is visible or the bottom part. So for the second for the second card and same for the third card and so on, right? So we need to try all possible cases. That's for sure, right? So that gives us a hint of a recursive or sort of a DP solution. Second hint is again the constraints, right? N is only till 100 and S is only till 10 to power 4, right? So a DP state of say something like n comma s that will be of the order of 10 to power 2 into 10 to power 4, which is 10 to power 6. It might work, right? This is for sure, and we'll see further into the solution like how and why are there overlapping subproblems. So as far as defining a DP state is concerned, so we define it as follows. We define DP of I comma j as consider first I elements is a sum equal j possible. If it is, dp of I comma j stores a 1, else it stores a 0. So dp of I comma j just means that we consider first I elements, and considering the first I elements is a sum of j possible or not, right? So coming to a final answer, in the question we had been asked, we need to find for the first n cards is a sum of s possible or not, right? So our final answer just becomes dp of n comma s, right? Now coming to defining the dp states, we define, say we have calculated for dp of I comma j, that is for first I elements, first I cards, a sum of j is possible, say, right? From here we need to calculate for the I plus 1 card, right? It can either be facing upwards or downwards, right? So one possible case is, now for the I plus 1 card, say it is facing upwards, so it will have a sum of j plus ai plus 1, right? And say it's facing downwards, then it will have a, so it will have sum of j plus bi plus 1. Okay, so this basically means that we have calculated for the first I cards and the sum is j, right? Now for the I plus 1 card, If it was facing upwards, it will have an integer ai on it, and if it's facing downwards, it will have an integer bi plus 1, sorry, ai plus 1 and bi plus 1, right? We are calculating for the I plus 1 card, right? So if it's having integer ai plus 1 on it, then a sum ai plus 1 gets added to the sum j, and if it's having facing downwards, then a sum of bi, it will have a sum of j plus bi plus 1, right? I hope this was clear. And if this is 1, then we can definitely reach here. So this is also 1 and this is also 1, right? If we can reach this state, we can definitely reach these two states as well. So that was precisely our DP transitions, and we'll understand it better by looking at the code. Okay, so here I have taken n and s as input and a and b as input as well, and define the DP vector of size n plus 1 comma s plus 1. And we have discussed the base case. So base case basically states that considering the first 0 elements, is a sum of 0 possible? Yes, it is possible, right? Just don't pick like just don't pick anything, right? Simply. Now we loop through all the cards and all the sum as well. If dp of I comma j is 1, then only it's point of proceeding further, right? Else it just means that we can't reach dp of I comma j, so we can't reach any further as well, right? And if we can read dp of I comma j, it's 1, right? Then the next state to consider is consider the first I plus 1 cards, and the I plus 1 card say has a of I plus 1 visible on it. Then this gets added to j, and the final sum is j plus a of I plus 1, and that we mark it as 1 since this was visible. So this can also be since this was reachable, so this can also be reached from here. Similarly for this one, so dp of I plus 1 comma j plus bi plus 1. So the I plus 1 card is facing downwards. So again, this can be marked as reachable, and we do only this when j plus ai plus 1 less than equal to s, right? Because otherwise it will just go array index out of bounds. As anyways, we are just interested in reaching a sum of s and not in say s plus 1, s plus 2, etc. So, and the final answer is just dp of n comma s, right? So we definitely have figured out whether it's possible or not, but we still also need to construct the answer as well, right? So let's say just print this dp vector and see how our table looks like, right? Okay, so this was our dp table, and we were solving for this test case n equals 3, s equals 11. The numbers written on the front part were 1, 2, and 5, and numbers written on the bottom part were denoted by t and top denoted by a h, right? Were 4, 3, and 7, right? And let's mark the indices as well. This was I equals 0, 1, 2, and 3. And for the sum part, this was 0 sum 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and sum equals 11, right? So first of all, yeah, since n comma s was 1, right? That's why we output a yes. And we need to construct the answer. So from n comma s, where can we go first of all, right? We can go to dp of n minus 1 comma s minus a of n, or dp of n minus 1 comma s minus b of n, right? Because on the nth index we could have the card could have an integer a of n on it or an integer b of n on it, right? So the previous state we just subtract a of n or b of n. We had discussed this in our dp states when we had defined the dp state. So simply dp of, we have s equals 11, right? So now for n minus 1, s could be like 11 minus a of n of I, or 11 minus 7, which is either 6 or 4, right? So from here we could reach dp of 2 comma 4, or we could reach dp of 2 comma 6, right? And since either of them are 1, we could have reached from here to here or from here to here, right? So we can just proceed with any of it. So yeah, let me just clear up the area a bit to keep it organized. So from here, say we pick this, right? So we have a s of 4, right? Now the card could have a integer 2 or 3 on it, right? So here the new s can be either 2, 4 minus 2, or 1, which is 4 minus 1, right? So from here we can go to dp of 1 comma 1 or dp of 1 comma 2, right? Both of them are possible. So that precisely means that from here we could have reached this state, or from here we could have reached this state, right? But since we have a 1 here, we could have reached from only here, right? Because if this was reachable, then only this can be ever reachable. So we just discard it, and that's we proceed with this. And yeah, so IS equals 1. And now the card can have integer 1 or 4 on it, right? So here S can be equal to 0, or the new S, Sn, whatever, can be minus 3, right? Okay, I guess this part is not visible to you. So, or S can be minus 3, right? So minus 3 is anyways like out of index, right? So let's forget that. That is anyways unreachable and marked as 0. So from here, I could have reached here, right? So how do we trace the path? First of all, from here, you could have gone here or here. And how did I get here? By choosing 7, right? So our 7 denotes to a T. So our final answer will have a T in the end. And from here, how did I get here? So I had a sum of 4, and say I choose 3, right? Then only I got to 1, because 4 minus 3 is 1, right? So again, since I chose 3, so again I write a T. And from here, how did I reach here? The card must have 1 on it, so that's correspond to H. So that's the sequence basically. How did we get a sequence? So we just iterated from here, and we checked how could have we reached here, right? From here or here, and what needs to be visible on the, should the card be facing upwards or downwards to get this. And that's how we computed the sequence HTT. That was one of the answers. If we had taken this part, we could have got a THH, right? And we could have outputted any of it. So let's dive into the code to understand it better. Okay, so yeah, this was just for outputting the table, right? So we don't need this now. So simply, if dp of n comma s was 1, if then only we have an answer, right? Else we just output a no, and here we just output a yes, and we have a vector answer, and we just fill it up from reverse. So we traverse from each card from n to 1, and if dp of I minus 1 comma s minus a of I, which we have checked, right? For if we are on the ith card, either we could have ai on it or bi, right? Say if it had ai on it, so the previous sums becomes s minus ai, right? That is from s minus a of I, you got to s by adding ai to it, right? So if this is 1 and s minus ai should be greater than equals 0, right? Or you can say s should be greater than equals a of I. Otherwise, just index becomes negative, and that's out of scope of an answer. So if that was the case, since you picked the card facing upwards, you add h to our answer, and just you go to the previous s, which was s minus ai, right? Else we just attach t to our vector, and since we chose to keep the card facing downward, so we subtract b of I from our s, and that's how we compute the array, answer array. And we had computed the array from backwards, right? We just reverse it and print it. And that was precisely our solution to this problem. I hope you must have understood, and I'll attach the code in the description. Thank you for watching us.